This is the second video on the technique, integration by substitution. And in this one, we're going to look at a couple of questions involving some trigonometry and some with limits as well. Okay. First example is integrate cos x sin x multiplied by 1 plus sin x cubed. And obviously, here's our problem. There's a function inside another function. It's not linear. Let's try u equals 1 plus sin x. Good idea as well when we do this, the derivative of sine we know is going to be cos, so we can already see that when we replace this function inside, part that's going to cancel with the derivative outside. Okay, so du by dx would equal cos x. So du divided by cos x would equal dx. Now we can start to replace inside the integral and see what happens. So we've got the integral of cos x sin x u cubed dx, which is du divided by cos x. Next step is to tidy up, see if we can take anything outside or cancel anything down. And clearly we've got a multiple of cos on the top, multiple of cos on the bottom, and we're left with sin x u cubed du. Still left with the next term inside, so at this point we can look back at our substitution, because remember we're trying to turn the full integral from a function of x and with respect to x into a function of u with respect to u. So if u equals 1 plus sin x, u minus 1 would equal sin x. And we have an integral just in terms of u. Just think about index form before we integrate this. So that would be u to the power 4 minus u cubed du, just by expanding this. And now we can integrate. Add 1 to the power, divide by the new power. Don't forget plus c. And very last step, there's no limits for this one, so all we have to do is, the original integral was for x, so our answer should be for x. So 1 plus sin x to the power 5, divided by 5, 1 plus sin x to the power 4, divided by 4, plus c. Example 2 says use the substitution x equals sine theta to prove the integral of 1 over the square root of 1 minus x squared with respect to x is equal to arc sine of x. If you've not seen arc sine of x before, that's just the same as sine inverse. You might see it written as sine to the minus 1 of x. The reason why we use the notation arc sine is because sometimes people get a bit confused with sine inverse and think it's 1 over sine. Like, it's not 1 over sine x, it's sine inverse. So it's like the opposite of sine. If you do sine and sine inverse, they like undo each other. It's like square and square root. They're the inverse functions, aren't they? So that's just the notation for sine inverse. Now we have actually differentiated sine inverse in one of the other videos on differentiation, and the result ended up looking like this. But now we're going to go the other way, so we're going to use integration by substitution to integrate this and show that we get to sine inverse. The first thing to notice about this one is the substitutions difference. Like, it's an x equals. It's not like the other substitutions we've been doing where it was u equals. So we've got to be careful with our initial derivative here. Okay. We will see more of these in further maths later on in the course, and there's other types of trig substitutions that we have to do for these inverse trig functions. But for now, I'll just do that. This is an example, and we'll go into more detail later in the year. So just be careful with your initial derivative. Like if x equals sine theta, we're going to have to differentiate with respect to theta, aren't we? Because it's a function of theta. So dx by d theta will equal cos theta. So dx would equal cos theta d theta. So let's see what we can replace inside our integral. So we've got square root 1 over, integral 1 over square root 1 minus x squared, so 1 minus sine squared. And dx is cos theta d theta. When you do substitution, which is for trigonometry, and it's like an x equals in terms of theta, you also want to bear in mind that we are going to be using identities on this question. So just bear that in mind. If you see a trig substitution, it's probably going to test your knowledge of the trig identities. And I know that sine squared theta plus cos squared theta is equivalent to 1. So if you look at what we've got here, it's a very common pattern when we do more of these. Like if you've got a square root of 1 minus x squared, as soon as I see that, I think of a trig identity. It just comes with a bit of practice and a bit of experience. Like that square root of 1 minus sine squared is the same as thinking about the square root of cos squared. So on top of this integral, we've got 1 times by cos theta, which is just cos theta. On the bottom of the integral, we've got the square root of cos squared, which is just cos theta. So tidying this up, we're actually just integrating 1 with respect to theta. And that's the great thing about these trig substitutions. Like you turn from something that you can't integrate into probably the easiest integral you'll ever do in the A level, but it's getting there, isn't it? Now just be careful. When we integrate 1 with respect to theta, it's not going to become x, it's going to become theta. So this would equal theta plus c. Now the final step, obviously we want to write it back in terms of x. So how are we going to do that? If we look back at our substitution, we know x equals sine theta. So what would theta equal? Well, if we take sine inverse, that would give us theta, wouldn't it? No, but you might be more comfortable writing sine inverse from GCSE, but we're just going to call that arc sine, because it's the same thing. So that would be the same as saying theta plus c would be sine inverse plus c. Next example, I've actually changed it slightly from the handout. I thought this would be a bit more interesting and better for a substitution. So we're going to integrate with limits, and we're trying to integrate x cubed divided by the square root of x squared minus 1. And obviously if this was just a question given to us, integrate, we wouldn't know we were doing a substitution, but hopefully we'd realise that we do need to do a substitution because of this function inside the other function. Okay, it's not 1 minus x squared, it's x squared minus 1, and there's also other x's involved, so we're going to just start by letting u equal x squared minus 1. Okay, I'll worry about the limits a bit later after we've integrated. So du by dx will equal 2x, dx would equal du divided by 2x. Substitute in and see what we can do. So we've got x cubed on top, square root of u, so that's u to the half on the denominator. Dx is du divided by 2x. So we're essentially multiplying two fractions together because this fraction and this dx is also a fraction. So we've got this stuff on the top, this stuff on the bottom. In terms of tidying this up, because it is important to tidy up as you go, if there's a multiple of 2 on the bottom, you can just take that outside as a half. And then you've got x cubed on the top, you've got x on the bottom, so we're left with x squared. U to the half on the bottom we can bring up and write it as u to the minus a half. Okay, so x did not cancel. No problem, let's just look back at our substitution. U equals x squared minus 1, so u plus 1 equals x squared, and we get a half. Multiplied by this. Get it into index form before we integrate, so expand this out. U to the 1 times by u to the minus a half, adding those powers, it would become u to the half, and u to the minus a half. Then we integrate. Add 1 to our power. Divide by that, so multiply by the reciprocal. Add 1 to our power, so that will become u to the half. Dividing by half, same as multiplying by 2. Okay, so this is the important bit. This is where there's like something slightly different. You've got two options now. Well, you've got three options, but there's two correct options and one wrong option. What you definitely do not want to do, right? Those limits there, those values are for the original integral. So those limits are x values. So you don't want to put the root 2 and the 1 into the u, because that root 2 and 1 represents x values. So we've got two options. We can write it back in terms of x, so we can replace it with x's, and if we replace it with x's, we can use the x limits. But I think it's probably a bit quicker if we leave it with u's, but just change the limits. So if x equals root 2, what would u equal? And just look at our substitution. So if u equals x squared minus 1, if x equals root 2, u would equal root 2 squared minus 1, which would be 2 minus 1, so u would equal 1. So we could say, well, if I'm going to write this with u's in, the u value will be 1. And similarly, if our original x limit was 1, then if we substitute into this, if x equals 1, we get 1 squared minus 1. So we could say u equals 0. And once we've changed our limits, we can, if they're u values, we can sub them back in to figure out what the actual value for the integral is. Okay, so 1/2. Sub 1 in, so 1 to any power is just 1, so that'd be 2/3 times 1 plus 2. 1 square root of 1 is just 1, minus, we're multiplying all this by a half, and then if you sub 0 in, I did pick this intentionally so it makes it a bit easier, but if you sub 0 in, you just get 0, don't you, for this one, because it's index form. Okay, so we would end up with 2/3 plus 2, which would be 6/3, 8/3, times by a half. And then you cancel that down, I think we end up with 4/3. Okay. Final example for this video, example 4. We're going to integrate pi over 2, 0, cos x, square root 1 plus sine x. And this is perfect for substitution. Like if you just look, function inside another function, differentiate, you get cos, derivative outside. Okay. So we just say, well, let's let u equal 1 plus sine x. Du by dx would equal cos x. So dx would equal du divided by cos x. Substitute in. So we've got cos x. Square root of u, so times by u to the half, multiplied by dx, which is du over cos x. Tidying this one up, really nice. Cos just cancels, so we're left with just integrating u to the half. Add 1 to our power, multiply by the reciprocal. And then the only thing we can really go wrong with on this one is just be careful with our limits. Okay. You could put it back in terms of x for this one. So instead of u, we could write 1 plus sine x and then sub in the x values. That would work fine for this question. I'm just going to show you how to change the limits. Okay. So if, don't forget these limits are x values. So if x equals pi over 2, u would equal 1 plus sine of pi over 2. And sine of pi over 2 is just 1. So u would equal 2. And if x is equal to 0, u would equal 1 plus sine of 0. And sine of 0 is just 0. So u would equal 1. So we're just working with the limits 2 and 1 for the integral in terms of u. So we get 2/3 u, which is 2 to the power 3 over 2, minus 1 to the power 3 over 2. We're not going to be able to get a fraction. This is going to be a third answer because it's a power of 2, isn't it? It's like the square root of 2 cubed. So if we think about that there, obviously you can use your calculator for this, guys, but that there is root 2 cubed, which is the same as 2 root 2. Okay, because that's like 2, or there's a couple of ways you can think about it, as long as you understand indices. It's 2 to the power 1 times by 2 to the power half, isn't it? Which is the same as adding the powers and getting 3 over 2. So I'm going to leave this answer as 2/3 times by this, so that would be 4/3 root 2 minus 2/3 times by 1. Okay. Hopefully that was useful and not too difficult to follow. Some of the substitutions do get quite tricky, but we will practice more of them throughout the year, don't worry. You're ready for exercise 4, guys, and that's the last exercise for this week. Make sure you check your answers using the answers in the booklet and the work solutions, which we put up on Connect. Okay, thanks guys.